Hello everyone, welcome to our senior design final presentation. Our project name is System Inertia Impact due to high renewable penetration. The team assigned to this project includes Michael Carbajal, Kimberly Guido, which is me, Shouran Liang, Manuel Rodriguez, Mayra Silva, and Alexis Vargas. Our faculty advisor and liaison is Ayman. For today, our agenda consists of project objective and background, the programmatic, case development, a case study analysis, the economic study, followed with a conclusion. I will first start with the project objective. A couple years ago, California passed the Senate Bill 100, targeting 100% carbon-free electricity by December 31, 2045. We conducted a study to simulate a high renewable impact using PowerWorld Simulator software, to then provide a suitable recommendation that would help reduce greenhouse gases into the atmosphere. So basically, the team will identify a threshold for renewable penetration in the system, a balance of load and resources for the on and off peak, the impact of change in short circuit duty, and the cost and system upgrades needed for this project. Now Manuel will talk about the work breakdown structure.
Thank you, Kimberly. So, hello everyone. I will now be talking about the work breakdown structure. So, when the team was handed down the PowerWorld case, here were the steps that had to be followed to achieve the maximum renewable penetration in California. First, the team studied and learned about the given student version case, which was set in the year of 2017. Then the team also determined the case assumption, such as determining the amount of load or generation for the year of 2045, which was 28 years from the given case. Also, as a team, we identified the system study scenarios, such as location of where to install the renewable generation. And from there, the team was able to develop two separate cases, which was the peak and the off-peak case. And so after completing the peak and the off-peak cases, the team carried on to conduct a short circuit duty and economic analysis to determine the cost of achieving high renewable penetration by the year of 2045. Here, I show a time frame of how the team identified the steps to achieve our goals. During the last year of fall semester of 2020, most of the research was conducted. First, we needed to understand what was inertia and the power system. Then, we needed to understand the dynamic models for solar, wind, and the battery storages. After that, we needed to understand the California power system. And carrying on to the spring semester of 2021, we started to develop the case. First, we had to identify the system, such as the amount of load, generation, number of buses, and transmission lines. And once familiar with our system, we continue with the load forecast, which is what our load will be looking like from the year of 2017 all the way to the year of 2045. Next, it was the case development for both the peak and the off-peak. After that, we conducted a steady state and transient analysis to ensure reliability of the system as we were modifying it. After that, we had the cost analysis to determine the cost, the short circuit duty studies, and last but not least, our report and presentation. And now I will pass it on to Kim with the project background.
Now I will go over the project background. First, I will briefly talk about the importance of system inertia. Since the US grid operates at 60 Hz, system inertia plays a major role in keeping the traditional generators running in case of failure. The stored energy that keeps the generator running is called inertia. Inertia is valuable to us in our grid because it allows mechanical systems to detect and respond to failure. Secondly, the problem with renewable energy in IPR is that renewables such as wind, solar, and energy storage power plants are asynchronously connected to the electric grid and are either entirely or partially interfaced through power electronics, referred to as inverter-based resources. Because IPRs lack inertia, renewable energy penetration in the system will cause under fault conditions by significant frequency deviations, leading to load shedding, machine and line damage, frequency instability, and blackouts by a cascading effect. And thirdly, in this project, we had to adhere closely with the WEC and NERC system performance requirement. WEC, which stands for the Western Electricity Coordinating Council, is a systems reliability that oversees the 9 states of the United States. When we conducted the study, we leveraged a couple of lead studies done by WEC themselves, such as the SITF research. And as for the NERC requirements, NERC meaning the North America Electric Reliability Corporation. So NERC is one of the most compliant requirements. We had to occasionally adhere to the TPL 001-4. We used the student version of the 2017 California electric grid through PowerWorld Simulator. Now, by looking at this map, we can see the existing transmission line along with the load and generation that is connected in this case. We evaluated the system to identify the existing issues before modifying the case to 2045. We also looked at the load and gen in this case to see if it meets the 2045 load forecast. Now Alexis will talk about our evaluation to a system's load.
To better understand what the 2045 load forecast looks like, the team referenced the California Energy Commission Integrated Policy Report, which was published in 2020. This represents the California energy demand in a 10-year planning horizon. And as you can see, the graph of the forecasted load, we have 3 plots representing the 3 scenarios, which are the low, the mid, and the high peak demand cases. A mid-demand case is modeled to consider a baseline scenario that averages the high and the low demand scenarios. So for example, the high demand scenario provides a high economic and demographic data, which includes a high rate of gross state product, or also known as GSP. And population growth and construction is considered at a high volume. And as a result of this scenario, we can include extreme weather changes because of higher presence of greenhouse gas emissions. But conversely, we have a low demand scenario, which considers a low increase in economic and demographic data and actually no impact from climate change. But to mention about why we have other factors that affect the load forecast, we have the transportation electrification, which will increase California's demand for electricity by adhering to Senate Bill 350. This demand also takes into account self-generation, where more residential and commercial areas are expected to have solar panels on rooftops, and therefore the consumption on the load will be brought down because of this. And finally, we also have the utility electricity rates, because they tend to vary because of availability of certain generation resources and their fuel costs. The team went forth choosing the mid-demand forecast load because it considers a baseline scenario at an increase that is more likely to happen. So since the CEC only gave their forecast until the year 2030, here we show the formula used to estimate the projection until the year 2045. The F represents the future balance, the P represents the present balance, and the portion of 1 plus I to the power of N will represent the annual load growth factor in our case. You can see in our calculation process that we took values from the previous slide, from the years 2021 to 2030, and then use the 28-year gap to account for the given case from 2017 to 2045. The final annual load growth factor, as seen in the bottom, was 1.17, and this multiplier would be used to multiply the load annually. To account for the load growth factor by multiplying each year from 2017 and on, we found the power demand to be 78 gigawatts by 2045. Comparing the difference of the 78 gigawatt and a total of 67 gigawatt from existing generation on the table, 11 gigawatts or more were needed to be generated by inverter-based resources. And on top of that, we see that 60% of non-renewable already modeled in the case. The team had to retire those natural gas units to meet 100% renewable energy penetration. Any resource from water, solar, and wind are renewable resources that we did not plan to retire since they were already renewable. We knew that in order to simulate the case to 2045, power generation and load would have to be consistently balanced by monitoring the slack bus, as it serves as a reference point to maintain the equilibrium of the power system. The map shown here is presented by the Renewable Energy Transmission Initiative, which supports the public process of California commissions and the independent system operator, also known as CAISO. The team was able to identify potential transmission to integrate renewable energy resources. From this map, because it provides different types of renewable generation that could be constructed in California, it also includes imports from neighboring states. The team decided to model photovoltaic and battery storage models in the simulation, totaling to 10 gigawatts in solar and 30.6 gigawatts of newly added battery in the simulation. Out of batteries total, we had about 26 gigawatts that came from retirement and replacement of natural gas units, and the remaining gigawatts came from modeling them in urban areas. Since California is a state known for its richness in sunshine, the Conversation Biology Institute had issued this map from the California Energy Commission to serve as an appropriate footprint for new solar renewable construction. We found this map credible to favor solar generation because of its abundance in solar voltaic projects as compared to other renewable resources. The legend on the bottom left gives you an idea of how much generation is available for modeling, and we were able to extract generation information corresponding to latitude and longitude coordinates. New battery storage models were added in urban areas since solar units were not appropriate for those areas. But again, the behind the meter self-generation of solar panels and also the self-storage batteries are already considered in the load forecast as part of the expected increase of microgrids from now until the future. In this slide, we mentioned how we developed a generator model into our case, but first I would like to explain what dynamic modeling even means in the power system. So to talk about dynamic stability on its own, is the ability for a power system to return to steady state or normal operation after a fault occurs. The dynamic models in a generator is what allows the generator to respond in a certain manner. So depending on the dynamic model, the response time of a synchronous motor in a generator can be measured by the starting success or the failure during the recovery process, as frequency of the generator attempts to stabilize after a fault. To describe a few of the dynamic models shown in here in the Venn diagram, we have the renewable energy plant controller and renewable energy generator converter models. These served for our solar, wind, and battery models in our case. A governor model would support a generator to control the flow of power input. The battery had a relay model for voltage and frequency protection. If the voltage or frequency were to deviate, the model would trip the generator so it can prevent damage. As these models were approved from the Western Electricity Coordinating Council, also known as WEC, which collaborates with California to keep the electricity system secure and reliable. We believe that the dynamic models still need improvement to provide a true representation of the results, as it is a real problem encountered by engineers when they compare with the actual generator infrastructure. We modeled our generators to have real power dispatched at a set point from a minimum to maximum, as well for the reactive power capability. The bottom right corner of the screen shows us the manner in which we connected our generator models into a point of interconnection, where then the power goes into transmission. This typical model is where we have the generator, a terminal bus, a unit transformer, and then the high side of the bus will then follow a point of interconnection. Now I will hand it over to Manuel, who will be talking about the steady state analysis.
Yes, so steady state analysis is the next step in evaluating the system during normal conditions and during contingency conditions. And reason for that is to ensure a more reliable system as we increase the renewable penetration in California. So therefore, the contingency analysis was conducted to find violations within our case so that when identified, we can fix in order to comply with the NERC requirements, such as the TPL-001-4. And precisely in this document, it states where our bus voltages must be within the range of 0.9 and 1.1 per unit voltage. And the power flow over transmission lines or transformers must be within the ratings of limit A and limit B. And so limit A will be the normal continuous rating, and limit B will be the emergency rating, which is approximately 130% of what limit A rating is. And so here I show an example of what an overload on a transmission line looks like in our simulation. The following overloads that are colored in red are red at 100% are lines that exceeded their MVA rating and were caused by a transmission line outage, such as a single line to ground fault, which was the most frequent type of fault that we've seen in our case. Here to the left, I show a visual simulation of when a fault occurs in our system. The gradients of blue color that appear in California is when a voltage dip occurs, and that is below the 0.9 per unit voltage. And the gradient red colors that appear in the visual are the rise of voltage above the 1.1 per unit voltage. And so since we must adhere to the voltage compliance and meet the criteria, we must keep the voltage in the white area to make sure our system is foolproof during the contingency. And so yes, batteries played a big role in solving our violations. The battery resources are utilized in areas where solar projects are not available. And by areas, I mean in the metropolitan areas like downtown Los Angeles, where solar photovoltaics cannot be installed, and that is by means of land or weather. And yes, weather plays a big role because we cannot place solar photovoltaics in areas where the sun is not intense. And so the battery resources were mainly used in congested areas and used as a solution to mitigate. And by congestion, I mean where a high flow of power is occurring in such places where generation is greater. And so the battery helps solve power flow issues. These issues include low bus voltages and overloaded transmission lines, especially during contingency conditions when an outage happens. And to the left, you can see what a battery looks like in the substation. And so as previously mentioned, the contingency analysis is a tool in the PowerWorld Simulator for analyzing steady state in our system. The contingency analysis will then create a list of types of violations at a certain location. Therefore, here's the list that we have for the number of violations and the solutions to mitigate them. And so we ended up having 82 voltage violations, which were fixed with 32 shunts and were also fixed with 11 batteries. And we ended up having 112 transmission line overloads, and those were fixed with 32 double circuit lines and were also fixed with 17 batteries. And now I hand it down to Michael to present the transient analysis.
Transient stability is the ability of a power system to return to normal after suffering a large disturbance. The large disturbance that may occur is the removal of a load, line switching operation, fault occurring in the system, or a sudden outage of a line. In our case, we tested 3-phase faults on major critical lines. The faults we conducted were for 4 cycles or 0.067 seconds at 50% of the transmission line. The duration of the fault was chosen based on a similar case done by WEC, which they called their standard disturbances. So these two graphs show our frequency result after adding the fault. The fault we inserted in this case was a 3-phase fault on a 765 kV line from Long Beach to Huntington Beach. This fault was applied at 50% of the transmission line. So on the left side, you can see the case converges and it shows the frequency is stable at 80% renewable penetration. And that is the last time the case is able to stabilize. On the right side, the case is at 81% and diverges. The large dip in frequency makes it harder for the generation to stabilize and causes it to diverge. So here is a visual for the change in frequency throughout California when a transient stability test is conducted. The visual is on the 80% renewable impact case. The system sees a change in frequency after the insertion of a fault. The areas that become blue are above 60 hertz, reaching up to 61 hertz, while the red areas show a dip in frequency reaching up to 59 hertz and below. So at 1 second in this visual, the fault was inserted, and at around 2.3 seconds, it begins to stabilize. And now I'm going to pass it on to Shouran for the off-peak case.
The off-peak case represents 2 a.m. during the winter time. The off-peak load will going to be only 40% from the peak load. During the off-peak season, solar PV generation will not be available. Battery that is supporting the system during the peak season will also be in the charging mode. This is the two table from the off-peak case. The left table is the off-peak load table. Since the battery will act like a load during the charging mode, so we need to add 11.1 gigawatt into the load table. All the battery in the same bus will be combined into a single load. When we are balancing the off-peak case, we don't find any other resources, so we need to put more batteries during the off-peak season to balance the load and resources. From this two tables, we can conclude that we are able to balance the case with 28% of renewable generation, and we need those gas units to provide the flexibility to charge the batteries. This is the ratio of the changing frequency when the transient stability is run. Right after the fall happens, the entire California is being affected. Within 2 seconds, the frequency is oscillating between 60.1 and 59.9 Hz. Then the frequency stabilizes after 2 seconds when the fall inserts. Next, I will pass to Kimberly to talk about the short circuit duty.
The team looked at the short circuit duty impacts as a result of the 2045 goal. If the short circuit duty reduced significantly, it will cause a major impact on the protection and the IBR settings. And here's a comparison of the years 2017 to 2045, single line to ground fault duty. To the right, you can see how the southeast and southwest have the most reduction in these areas. Now, as a second test was made, there was a different fault inserted, which happens to be the least common one, but most critical to the electric grid. That is a three-phase balance fault. And again, if you look at the graphs to the right, you can see how southeast and southwest have the most reduction in these areas. As a result, the California areas such as southeast and southwest have a total reduction of 1.7 gigaamps and 2.7 gigaamps. Short circuit analysis showed a decreased fault current in areas where the gas resources were mostly retired. This is why we see in the southeast and southwest have the most reduction. Because of our analysis, we recommend further evaluation in the protection settings for both those areas. Now, Mayra will talk about the cost analysis.
Thank you, Kimberly. The transmission line and voltage. An economic study was performed to absorb the estimated cost of required per unit infrastructure for the thermal overloads on transmission equipment and overvoltage and undervoltage at the substations. To avoid machine damage, generator stripping, its load shedding, and occurring any blackouts. To achieve a 2045 goal, it was determined that the system will require the addition of 36 new transmission lines, along with a few shunt capacitors and reactors for a cost of $20 billion. The study also included the addition of voltage support will be required for a total of 32 cap banks and 8 SVCs for a total cost of $32 million. The final overall cost is $40 billion. The team utilized both the 2021 PG&E and PSEE proposed generator interconnection unit cost guide found on the California Independent System Operator website. I hand you off, Kimberly, for the conclusion.
Thank you, Mayra. Now I will quickly summarize and conclude our senior design project. For our on-peak case, we can meet the 2045 California goal by only allowing 80% renewables, and anything above our recommended threshold will require additional study. For the off-peak case, we will have to stagger the battery charging, given that we have a limited amount of resources. The short circuit duty test conclusion was that we would like to have the protection engineer make a further evaluation in the southeast and southwest areas of California. For renewable dynamic models, we concluded that the dynamic models in simulation need further improvement to represent the actual generator model. And lastly, for the cost analysis, it was concluded that it will total to an amount of $40 billion to make this project. Thank you, everyone.